is more than is larger than the speed of the rotor. But in the generator mode,
This rotary speed
is
is high.
equal to that. The speed of the rotor, the squirrel case, is more fast. It's more fast.
This rotor speed is fast of than stator speed.
So we can see that the inside is fast, the out is
Slow.
slow. Yeah. So this is the two modes of the induction mode. We also have the third mode is the braking. So this S is from 1 to 2. So in this mode, the rotor rotates opposite direction. You see. So here, the omega R is opposite. Opposite is the omega E. Yeah. So the two direction is opposite. But in another two modes, yeah, the direction is the same. The motor and the generator, they all are the two directions are same. Yeah. Omega R and omega E. But in the plugging mode, so the omega R is different from the omega E. So it's the difference between them. So it's why this happens? Because sometimes the supply phase is changing suddenly. So the direction of the flux will change, but the rotor will rotate at zero. So at this time, it will quickly stop the rotor. Yeah. It will quickly stop the rotor, just like it's braking. So it's the characteristic of plugging mode. So we usually use it as braking application when you want to brake the motor. Yeah, we can just reverse the sequence of the source. Yeah, then we can reverse the flux. Yeah. Then the rotor will quickly stop. The method is changing the power supply. So this is the plugging mode. Let's have a review the three operation modes of induction. So we should know that the direction of the NS and N, yeah, the direction of the flux and the direction of the rotor. In three modes, they are different. Yeah. In the braking, we see the NS, NS, and NS is here. But the rotor speed is opposite. So in braking mode, in braking or plugging mode, so the two directions are opposite. But in the other two modes, directions are same. Yeah. So this speed, direction of speed. Also, we should know the direction of the torque and the rotor speed. The torque we see here. the torque in plug-in mode, the speed of the direction of the torque and the direction of the rotor speed, so they are opposite. So it can break. Break the rotor because the torque's direction is different from the rotor speed, so it can stop the rotor. But in the other two modes, the direction of the torque is the same as the direction of rotor, so it can make it rotate. Just as the motor, so the speed of the rotor is slow. It's slower than the synchronous speed. But in the generation mode, the rotor speed is faster than the synchronous speed. So these are the differences between them. We should just know the direction of the speed and direction of the torque. We should know this. Although there are three operation modes. But machines are mainly used as motors. They are usually used as motors. These three are our motors. We have studied the advantages of the induction machine. So also the three important aspects. For one, for induction machine or induction motor, we do not need a DC field current, because the current of the rotor are induced. So we do not need a DC current, so it's advantage. And also the motor is cheap. The structure is simple, material, and not so complicated. So it's cheap. It's inexpensive, and in many applications, we can use the induction motor to replace the DC motors. Many applications, about 80 or 90% of the applications, the LC of the induction motor can replace DC motor. So this is why we mainly use the induction machines as motors. But sometimes we can maybe wind plant in the mill, high hydropower. Maybe these two applications, induction machine can be used as generator. For this, why we use it as generator? Because although it was not widely used, but for low power, we can also use it as generator. in wind and hydro, we have some methods to control it. Just as this slide. This is storage of wind engineer. Yeah, this is the turbine. Turbine, and this is the induction machine. Also, always it has six terminals, so it's one rotor. So it's one rotor. Yeah. The main terminal is connected to the tower, and the road, the terminal of the road is connected to. You see, this is a converter. Yeah, this is a back-to-back converter. So use this converter. We can control the frequency of the stator. Yeah. So also we say this is double fed induction motor, double fed induction generators. We know today many of the wind turbines for high power we mainly use permanent magnetic for synchronous machine, permanent synchronous machine. But for small power, but for low power, sometimes we use the induction machine because it's cheap, cost is low, and small size. So only for the small size, so we can use the induction motor. But for high power, we don't use it. This is in detail. So we can see that this turbine, this is the gearbox, mechanical gearbox to change the speed, and this round rotor induction generator. The bank-to-bank converter is here. The left we call it the inverter. The right part of the bank-to-bank converter we call it rectifier. So uses electronic device. We adjust the resistance. We adjust also the current frequency of the rotor. And the same, we can control the current of status.
Sir, this rotor speed is greater than propeller speed.
No need. Because we can change the speed in the rotor. So when the rotor is low, we can do a positive AC, AC current in positive synchronous. But if the rotor is speed is high, we can do negative synchronous. So we can just adjust the current, the frequency of the current. If the rotor is just at 50 or 60 hertz, so we will give the DC current. to the rotor, so it can work at a wide speed, from low to high. It all can work. So it's called double reflex induction motor. So for this for only for small size platform, but for high power we use the permanent synchronous generator. The synchronous generator we will learn at chapter 5. Chapter 5. We'll learn synchronous generator, also the permanent synchronous generator. Okay, and these are the operation modes of induction machines. That's three modes. Let's learn the first part. The first part is the electromagnetic relations. We know the road current, the frequency is sleep multiplied by S. Sy is the synchronous speed, speed of frequency. So this is we know this, and also we know the road flux rotate, and the stem speed also is synchronous speed. We can see this. This is the synchronous speed. The N is the rotor speed. So N is less than Ns, and the delta N is sleep speed. So when the rotor rotates, the two speed and the two speed is equal to the synchronous speed. So we see the two fluxes. You can see this. The blue one is flux, and the purple one is rotor MF. So they are rotating at the same speed. Both are the synchronous speed. So then they can enact to generate the torque to make the machine rotate. So we should know the two fluxes have the same speed. All are the synchronous speed. Then the two MS, one for flux and another for the rotor MS. Let's just see the two. This is flux for two cases. For A case is that the leakage for one this the leakage inductance is very small. The rotor's leakage inductance is very small. Then there's no Lang degree. So the current of the rotor and the voltage of the rotor, there's no power band angle. Yeah. So in this case, is idealized situation. So the angle between the two MF is 19 degrees. So it's very good. But generally, the inductance the leakage inductance is not zero. And this time there will be a power factor angle by 2 between the current and the voltage induced in the rotor. So the MF of the rotor is another angle by 2. So in this case, so the angle between the two fluxes is not 90 degrees, not 19. It's not 90. It's just a power bank angle. So these are the two situations. So we have learned the operation modes and the electromagnetic relations. We should understand the principle. Understand the principle of this and understand the relationship. So these are important for us to understand the other parts of other parts. Yeah. So let's study the fifth part, the equivalent circuit. This is the most important of the AC machine. We will present the equivalent circuit of the induction motor.
Sir, you didn't send this PPT. You didn't send this PPT.
Oh, okay. We'll give it
the second part.
Yes, we'll do it. We see the left graph is schematic of the induction motor. Yeah. We just think inside the rotor. It can be dislocate or one rotor. No problem. In principle, the three phase have three windings of the state, but the rotor windings are shortened. And here are shortened. Although it has three phases, but if we can use the single phase, equivalent circuit for analyze the principle of the machine. Use only one phase of the circuit. But let's see. capacitor, we use any phase. A phase is okay. One state, one rotor. We can based on this graph, we can build the equivalent circuit. Like this. Left is the graph, and the right graph is
equivalent
primary circuit. So R1 is the resistance of the state winding, and the X1 is inductance. So we can calculate the X1 equals 2 pi F1 A1. F1 is the frequency of theta constant, frequency of the flux, frequency of the source, power source. And also calculate X2. X2 is equal to F2 L2. F2 is induced in the frequency of induced current in the rotor, and L2 inductance.
Is rotor is short circuit already?
Yeah, just like it's squirrel cage. So it's shortened. R2 is the resistance of the rotor, and X2 is the leakage inductance. We can use this simple circuit to present the induction machine. But only this is not enough. We can just know the principle, but we can't calculate the parameters. We can't because there's magnetic is not linked, connected together.
What is capital M?
So there's also a mutual magnetic induction. So when a current follows in the rotor coil, there's if a current flows in the rotor current, it will influence the current in the state. So they are complicated relationships. So we have the methods. We can modify the circuit. This is EMF. We know the EMF of the rotor. We can calculate it with this equation: 4.44 N2 F2 then P. Just display. Okay, where is the flux? Flux density. N is tens number. So we can calculate the EMF of rotor. We see here the F2. We know F2 can equal to S multiply F1. F1 is the frequency of the stator. So we just replace the F2 to S F1. Yeah, it's like this. We replace F2 to S F1. So we get the second equation. And we know this part is E2. E2 is for the frequency of the stator F1. So we should know the difference between the E2 and the E2S. So it's difficult to understand the differences. I can just explain that E2 is for the frequency is for stator frequency, and E2S is for the sleep frequency. It has S here, so E2S is for the frequency of rotor. So like this, we know E2 is the function of F1. E2 is the function of F1, but E2S is the function of F2. So this is the difference between them, and this is important to understand the other equations. This transformation allow us to connect later the rotor and the stator circuit. We can connect it together. As here, it's not connected. Yeah, it's just two coils. Yeah. The electric circuit is not connected. But use these transformations, we can connect the two parts of the electric circuit together.
Refer to high side and refer to low side.
Okay. Also, just similarly, we can get the X to S is the inductance, X to S and X2 at X2. The relationship is similarly. The X2 is the function is a function for F1, and the X2S is a function for F2. It's for the rotor the sleep frequency. So we just relationships. This is a rotor equivalent circuit, a single phase circuit. There's a current I2, current I2. Use I2 can be calculated by this equation. SE2 is the voltage. SE2 divided by the R2 resistance of the rotor circuit plus X2. X2 is liquid inductance. So we can use this equation to calculate the current I2. And we have then we have divide the denominator and the numerator. The numerator and the denominator, we both divide them by the slip S. Divided by some S. So this equation will change to this equation equal. So the S E2 is changed to E2, and the R2 is changed to R2 over S. No S here. So we'll obtain this equation. So the corresponding current the circuit is this one. Is this one. The voltage is E2, and the inductance and the resistance are changing. The two circuits are equivalent. And moreover, we can represent the equivalent rotor resistance R2 over R2 over S. Here, the R2 over S. We can divide it into two parts. Just this one and this one with this equation. R2 over S equals R2 plus R2 multiply Y minus S divided by S. So just use this equation. So the R2 over S is divided into two parts. So these two circuits are equivalent. We know the R2 is the constant value. R2 is the constant value. But another this one is a function of S. So we divide this in two parts. Constant is variable. The function of S. The R2 is corresponding to the losses, the copper losses of the rotor, and this part is corresponding to the mechanical load and the mechanical loss. So now we have built equivalent circuit for the rotor circuit. It's just for the rotor. So it's just for the rotor. It's the rotor circuit. Which is how frequency the frequency here, the frequency is the same like the status supply frequency. So, the frequency here is F1. Frequency here is F1, but the original the frequency is F2. So we change the F1 or F2 frequency to F1 frequency. So, but they are equivalent. So the rotor circuit, is based on the static frequency. Okay. We have previously we just changed the rotor circuit, but we have to resolve the stator circuit. So this equivalent can be changed to this one. So it's the real equivalent circuit of the whole machine.
This coming to high field cell. This coming to high cell. I mean, this is the low cell and this is the high cell. So this coming referred to high cell.
See, the frequency is the same because we have changed the frequency to F1. The frequency here is F1. The frequency here is also F1. The two frequencies are the same, so we can connect the two circuits together. If the frequencies are different, so we can't connect the two circuits, but use the rotor's equivalent circuit. We changed the frequency of it. So here the frequencies are the same, so we can just connect it together and replace just connect it together. We obtain this equivalent circuit.
Sir, can I draw it without excitation branch?
No, this is
In transformer, I draw it without excitation branch.
in transformers. Maybe we can do this.
Yes, but why we can't draw this equivalent circuit without excitation branch?
They are air gap, and they are air gap. So it's different from the transformer. It's different from transformer. So the common link here consists of magnetic core. The loss RC represents the magnetic core loss, and also magnetizing reactance. We call it XM. The two windings, the state windings and the load windings, they are coupled. They are coupled magnetically through this air gap. It represents air gap. So it's different from the ideal transformer. So by transferring the rotor parameters to the state side, we can get rid of the magnetic coupling. We can get rid of the magnetic coupling. Just connect the two circuits together. This equivalent circuit is very similar. It's very similar to the one we have learned in chapter 2. In chapter 2, the transformer equivalent circuit. It's just very similar. Okay. We can use the four equations. The four equations to change to calculate the parameters here. So the parameters are different. Here is x2, here is x2 prime. x2 prime. So we can use these two equations, the four equations to calculate the parameters. E2 prime, x2 prime, and also the resonance R2 prime, R2, yeah. So they all can calculate by these equations. The N1 and N2 is just the effective turn rate. This is the turn ratio. The turn ratio. That's the turn ratio. As we have seen earlier, the rotor equivalent resistance R prime 2, over S can be split into two parts. The R2 prime is constant, and this is a function of slip. So the equivalent circuit can be represented again as showing here. Just use this expression from the up to the top. They are equivalent. So each part of the equivalent circuit represents one part of the machine. Each part of the circuit represents one actual part of the machine. For instance, for example, this part represents the stator winding, and is equivalent to the transformer prime winding. Also, it's the state. Represents the state winding, and this part represents the rotor, and equivalent to the transformer's secondary winding. Finally, this part is important. This part represents the mechanical load, and also the mechanical losses. So you can clearly notice there are remarkable analogy. Between the equivalent circuit of the transformer and the induction motor. So there are remarkable analogy between them. So we have learned off, and we finished the class.
Okay.
Should we do this please?
No. We can continue.
So no break next. No break.
In summary, the complete the complete per phase. This is the complete per phase equivalent circuit of the induction machine. Showing here, we have 4 parts. Yeah, we have just learned it. So this is the state circuit. This is represents the air gap. And this is the rotor circuit. And this is the load and losses.
It's like transformer.
It should be noted that we use the per phase equivalent circuit. But for a real machine, it's three phases. So we should change it. When we calculate the power of the voltage, we should change the values. For instance, the V1. The V1 we know is the phase voltage. But in a real machine, it just gives us the line-to-line voltage. So there's a square root 3 relationship between them. Yeah. And also the power. We use this single phase circuit. We can only calculate the power of one phase, but if we want to calculate the whole power of the machine, we should multiply by 3. So we should know that. We see this circuit is a little complicated. In the transformer, we have a meter here, but in the induction machine, we can't do this. But we also have some simplified method. We can simplify the circuit of the equivalent circuit. We can simplify first. This is recommended equivalent circuit. The core losses, this one, RC is removed. So the core loss is removed, but the copper loss, R1, the copper loss is still considered in the calculation of the efficiency. So this is the RGB method. Yeah, just remove the RC. And the second simplified type equivalent circuit, we just move the R1 and X1 from here to here. It's also called the pi type. It's called pi type equivalent circuit. The assumption is that the voltage, the terminal voltage, V1, the terminal voltage is much higher than the voltage drop on the resistances, because the V1 is much higher than the voltage drop on this part. So we can move the shunt, so we can move the shunt branch from here to here. By using this equivalent circuit, we can also simplify it further. Like this. The R2, R1 and R2, X1 and X2. Yeah. The four parts we can make them together like this. So the X EQ equals to X1 plus X2. Yeah. And the resonance REQ equals to R1 plus R2. This makes the circuit more simple. So if you use this circuit, it's more simple for us to calculate the parameters. Here, the road current can be calculated by dividing the terminal voltage V1 by the series impedance. So this impedance representing the stator and the rotor together. So this is the gamma type of simplified equivalent. This is also to the similar to the transformer equivalent circuit. Yeah, it's also similar. So this equivalent circuit, and also we can start the power and torque equation. So from this equivalent circuit, we can calculate the power of the gun equals to Q. Q is the number of phases. Q. Square R2, the R2, I2, square I2 and I2 over S. So this is the power. Transferred across the air gap. So the air gap is this P gap. And the example is the textbooks. So this is the air gap, and this we also calculated the rotor loss. Square I square R, the rotor loss. Use this equation. Also, here is the number of phases. And the electromagnetic power, MECH. The electromagnetic power is the difference of the P gap and the P rotor. So just use the two power. The air gap power plus the equations here. So it's a function of also it's a function of sleep. Yeah. So the electromagnetic power is a function of sleep. See, this is similar. Is an alternative form. Just divide the R2 over S. R2 over S. Divide into two parts. We have later earlier. The two equivalent circuits. Both can be used to calculate the parameters. Let's have example of our textbook. On the textbook, example 6.1. 6.1. This is example. Three-phase induction motor. Two-pole, 60 Hz. Speed 3,502 RPM. The input power is 15.7 kilowatts, and the terminal current 22.6 amp. Yeah. So we should calculate. We should calculate the loss. The root loss. Yeah. So we can use this circuit to calculate it. We know the hour. Yes. We know the hour. And we know the IEP. The power, the input power.
So this answer is on and is true.
That's it. So
oh, this three is
So let's see. So the stand power. The power is displayed. So it should be noticed that is this says number 3 here, because this is 3 phases. So if you forget this, the value will be wrong. So this is it. Just use the equation. Can obtain the P state. And this is simple. The air gap power, just the two power, the difference of the two power, the input power, plus minus. So this bring me value 0.3. This is okay.
0.3 kilowatt.
So no need to write it and point 0.3 or 0.6. No need to do that. Just like this is okay. Let's see the speed, the synchronous speed from the equation for chapter 4. We are very familiar with it. Just OS also we can calculate the slip. Yeah, calculate the slip. Calculate the slip is just the NS, N, and NS. You can see its slip is very small. It's very small. Use equation. You can also calculate the root power. It's just equals the S by the damp the air gap power is 400 watts. So this is a simple example of 6.1, and there are also a practice after the example. You can do it yourself. So let's see how to calculate the torque. Calculate the torque. The torque is similar similar to the calculation in DC machines. Is similar to DC machines. Torque equals to the power divided by the speed in radians. So this is the torque calculation equation. Just by this. So omega s. We should know that the power on the shaft. Is not equal to the power of electromagnetic mechanical power. There's a loss. So if we should calculate the power on the shaft and the torque on the shaft. Use these equations. It should be remove the loss. Remove the power of the loss. So we can have a conclusion here. The core losses be neglected. So the person so the circuit is here. In this case, the calculation using these two equations to calculate the power, air gap power, and the mechanical power. Okay, let's finish.